Hello, everybody. I hope you're doing okay. My apologies if the audio is too loud or too quiet. One of my kids is sick, so I am home today with her. There's a couple things to do today. One is this thing called Notes for March 23rd, 2022. That's the first thing you're going to do while watching the video, and they're going to look like this. Whoops, let's go to the first slide. They're going to look like this. The second thing you're going to do is an assignment called Introduction to Energy. It looks like this. Don't worry about the fact there's 26 problems. It's not going to take you that long, I promise. But it will take you probably the rest of the class period today. And I did highlight to do it on a piece of paper. It's just easier to do on a piece of paper. You don't have to write the questions and answer the questions. Just put the answers on a piece of paper. That's all you got to do. All right? So once you've got this thing open, you're going to go through and fill it out with me. And I'm going to fill it out right now. All right, I even put that right here. And the notes are about work, which we talked about yesterday in class. Power, I think we may even skip for the day. I had 3 or 4 slides on power and then I decided to cut them out. We're going to do a lab the next time I'm there called Power of a Push-Up. You're going to have a couple group mates do some push-ups and we're going to track your power output over time. Work and power are very closely related. And then the new thing for today is energy. So what is energy? Well, to figure out what energy is, we got to go back and talk about work real quick. So work is two things. Work is force times distance. That's the most basic equation for work. The second equation for work, if we think about force as being mass times acceleration, well, let's just write that. Work is mass times acceleration times distance. I think I want to put spaces in between my multiplication signs. That makes it look a little bit better. Yeah, there we go. So work is force times distance. It's also mass times acceleration times distance. If I was to put a sentence definition for work, I would say it's a measure of the energy transferred that occurs when an object is moved over a distance by an external force. So what does that mean? You kick a ball, which 100% of us have done at some point in our life. You're transferring energy from your leg to your foot to the ball. Or if you're throwing something, you're throwing a football, a baseball, a frisbee, whatever it is, you're transferring energy to the ball, making the ball go throughout the air. All right, there's 2 units of work. You can fill out slide 3. You can go back and look at what you wrote yesterday for that. One of them is the metric unit of work. The other one is the imperial unit of work that we talk about when we talk about exercise, we talk about food. So you can go and you can fill that out on your own. The concept of work is pretty much the same thing as potential energy. So what do I mean when I say potential energy, or what do we mean when we say potential energy in general? Potential energy is energy that's stored and that you can use at some point. So the way we use potential energy on a daily basis is probably by gasoline. Most of us probably ride in a gasoline-powered car for the time. Now, when you're 35 years old like me, you're probably going to tell your kids, oh, we used to ride in gasoline cars, but now we ride in electric cars. But for the moment, most of us probably ride around in a gasoline car. But gasoline is energy that's stored in the gas tank, in the chemical bonds of the gasoline, and it can be used in the engine to drive the car forward, make the air conditioning and the heater work and all that stuff. A form of potential energy 100% of us use is food. So there's a lot of energy in food, way more than you might think. Way more than you might think. And of course, we use that energy to think, we use it to walk, to run, to do push-ups, or do whatever. Okay, so gasoline and food, ones that we use probably on a regular basis. And then the third one we also use a lot, the potential energy stored in a battery we use constantly too. You're probably watching this on your Chromebook or on your phone or something like that. And there's a lot of chemical potential energy stored in the battery. So potential energy, all it is, energy we can use, but for the moment it's being stored somewhere. And there's more kinds of potential energy than this, but that's just a good intro. All right, slide 5. Kinds of energy in physics. Energy is the capacity to do work. And the kinds of energy that we're going to talk about here a little bit throughout the year. We're not going to talk about every kind of energy in the universe. We talked about potential energy. It's energy that can be used. There's kinetic energy, which is the energy from movement. So you're running at 10 miles an hour, you're sprinting at 15 miles an hour or something like that. You have energy, and it's called the kinetic energy. Thermal energy is the energy of heat. So you heat up some food, it's hot. We call that thermal energy. Nuclear energy is a little bit more complicated. Not a ton more complicated, but nuclear energy is the energy stored in the nucleus of an atom. We can get that energy out to do things like take an X-ray of your bones, to power a nuclear power plant. The sun uses nuclear energy to work. There's elastic energy. Elastic energy is not really complicated, but there's a lot of different ways elastic energy manifests in the universe. We're going to make mousetrap cars if we can. I got to gather all the stuff for it in about 2 or 3 weeks, and the elastic energy will power our little cars. Elastic energy is the energy from springs, or maybe your socks have some elastic in it, and when you stretch out the sock, it snaps back to its original shape. The soft tissues of your body, like the tendons and ligaments, have elastic energy in them, and your muscles can be loaded with elastic energy too. There's electromagnetic energy, and that's the energy of light, or radio waves, or X-rays. There's chemical energy, like the energy stored in gasoline or food. That's chemical energy that can be used to power us or power a car or whatever. And there's some more that we're not going to list, mostly because I ran out of room. All right, on to slide 6 here. Slide 6 talks about potential energy, and it's worth pointing out that we don't really need to know anything new to master potential energy. We already know what we need to know for potential energy, and that's because potential energy and work are virtually the same. So we had 2 equations for work. One was that work is equal to mass times acceleration times distance, and then the other one was force times distance, and those are both fine. The potential energy equation, I put PE for potential energy because I don't really want to write the whole word out every time. If I'm talking about the potential energy from gravity, maybe what we should do together is put a GPE, because we're talking about the potential energy from gravity. So the gravitational potential energy is equal to the mass of an object times little g, that little g is from the first term, times how high it is off the ground. So let's compare that to the work equation real quick. This is acceleration A. G is the acceleration due to Earth's gravity. D was just the distance. It could have been left, right, up, down. We didn't really specify. H is specific for height. How high off the ground are we? All right, so virtually the same thing. Virtually the same thing. Let's do a few examples here. I got 2. Neither one is super complicated. Potential energy example number 1. If we are 20 meters above the ground, and this is not the ground, this is a swimming pool, and our mass is 50 kilograms, how much potential energy do we have? Okay. So there's a few ways to think about this. I think I'm going to make my font 22. That way we've got plenty of room here. All right, so GPE. Let's just write the equation. I'm pretty simple here. I like to list things out. Gravitational potential energy is mass times gravity, the acceleration due to gravity, times height. All right, so we can figure that out. What was M? M, let's see, I'm going to highlight the mass in the same colors here. M was 50, and I think I'm going to make you yellow. G was 9.8. It's always 9.8 as long as you're on the Earth. Let's make the height above the ground. Should we make it blue? Because that pool has kind of a blue tint. Cornflower blue. Let's just make it regular blue, yeah. So the height above the ground is 20 meters. Okay. So M was 50. G was 9.8. And then our height above the ground was 20 meters. All right, so GPE, looks like we got to math all that out. I can't do that in my head. 50 times 9.8. Whoops, why am I hitting minus? What am I doing? 50 times 9.8 times 20 is... There we go. 9,800. Okay, so 9,800 joules of energy. And remember, we talked about this yesterday in class. I didn't write the units in here. Probably should have. If there's a physics professor looking, they're going to look at this and go, I can't believe this guy didn't write the units, but that's okay. Once we get to the final answer, we want to think about what it is. If this is potential energy, we want our unit to be in joules, so we'd say capital J. All right, so that's not so bad. We can do that. These ones really aren't the worst thing in the world. You've got potential energy right now. I'm assuming that you're sitting in a chair. Maybe you're sitting on a lab stool. Maybe you're at home sitting on your bed. I'm not sure. But for most of the chairs at school, they're about 0.4 meters above the ground. So here we go. We're 0.4 meters above the ground. I just made up a mass. I like round numbers, of course. 50 kilograms is the mass. And then how much potential energy do we have? All right, so I'm talking about gravity here, because you're above the ground and gravity will pull you down. Not MPG, MGH. All right, so let's see. What was our mass again? 50. And then G is always the G. We're not on Mars or anything, so that is what it is. And then we're going to get an answer here. Let's see if I can actually type it into the calculator correctly this time. 50 for our mass times G for 9.8 times 0.4. We have way less potential energy. If my math is right, it's 196 joules. All right. All right. So that's not so bad. For the GPE, sometimes you might have to figure out how high something is if you know how much GPE it has, but other than like the process is pretty much the same thing. There's another kind of energy we're going to talk about today, which is not really that much more complicated. There's a squared in here, and we'll see that in the equation. It's called kinetic energy. So kinetic energy is a little bit different. I don't know if it's that bad though. Like we said in the fifth slide over here, it's the energy due to movement. And the equation is Ke for kinetic energy is equal to 1/2. The 1/2 is just fixed in the equation. It's just always there. 1/2 times the mass of whatever is moving times the square of how fast it's moving. So you have to remember to square the velocity. Don't forget that. I'd say that's like the number one thing people forget when they're trying to figure out how much kinetic energy something's got. All right, so here we can tell this beautiful piece of art is definitely something I would create. Our first question says, if a person and skateboard are 75 kilograms and are moving at 15 meters per second, what is their kinetic energy? All right, so is this also going to be super bad? I don't think so. I like to write the equation out, as you all know by now. Ke is 1/2 mv squared. If you're going to write it out like me and you want to superscript these things, you can do the keyboard commands, or you can just highlight whatever you're going to superscript and then go to text superscript. And oh, wait a minute. I think the whole thing was superscripted. Okay, there we go. That was weird. That was weird. You'll probably have the same thing on your keyboard too. You can hit Control and then the period button and it'll superscript as well. All right, anyways, back to the problem. Ke is 1/2. The 1/2 just goes into the equation. Times the mass. Mass is always in kilograms when we do these questions, and our mass here is 75 kilograms. Times the velocity squared. We are moving at 15 meters a second. 15 meters per second, and it's squared. All right, so everything is set up into the equation, and let's see if we can get an answer here. All right, I don't know when I do the screen cap if you can see my calculator, but my calculator is here to the left. The calculator on my computer is kind of annoying to plug things into, so I don't know, it'll be okay. All right, so let's do the 15 squared first. So 15 squared is 225. times 75 times a half. I think I'm going to use 0.5 instead of a half. That'll make my life a little bit more tolerable. And if I've plugged everything into the calculator right, it looks like we have 8,437.5, 8,437.5 joules, because it's energy, of kinetic energy. One thing I notice when I look at the kinetic energy equation is that the velocity is really important. Why is it really important, you might ask? Well, it's really important because it's squared. It's squared. If I was to double the velocity, what would happen to the kinetic energy? So let's say the person is the same mass. It's the same 75 kilogram person. But instead of going 15 meters a second, we doubled their velocity to 30 meters a second. Well, because the velocity is squared, the kinetic energy wouldn't double. Even though we doubled the velocity, the kinetic energy would not double. It would actually go up by a factor of 4. So if I think about the kinetic energy equation and I think about the most important thing that's going to affect how much kinetic energy something has, it's probably the velocity. All right, we got one more example here, and this one's a little bit different. So in this one, we have some object. What is it? I don't know. I thought about like making a picture of a bird over here, and that was taking me like 10 minutes, and it was still a terrible picture. So I just put an object so I didn't have to draw anything. The object has 12,000 joules of kinetic energy, and it's moving at 12 meters per second, and we're asked for what the mass is. And that is a more complicated problem. More complicated for sure. Let's see, there we go. So again, I like to start out by writing out the equation, just to make my life as simple as possible. mv squared. Again, it's probably easier to do this on paper, but I can't today. All right, so let's see. Today we know, or not today, in this problem we know the energy. So 12,000 joules is the energy, and it's equal to, let's see, 1/2, and then 1/2 is always there. I don't know mass. That's the challenge in this problem, because the problem says, what is its mass? Ooh, okay. I do know that it's moving at 12 meters per second, and that, of course, is squared. Don't forget the squared. Someone out there will. It's okay. With practice, you'll be okay. All right, so we get here, and again, this is easier on paper, but that's okay. If I'm looking for m, right now, m is multiplied by 12 squared, and it's multiplied by 1/2, and we're going to do our best algebra here, and we're going to think, well, wait a minute, if that's multiplied by, if a variable is multiplied by some numbers, if I want to figure out what this variable is, I got to divide by those numbers. So let's see if I can do this on a computer. I don't really like doing it on a computer, but that's okay. So I got to divide not just by 1/2, but I also got to divide by 12 squared. And I remember saying in class yesterday, whoops, that some people, oh no, formatting is not going to, oh no. All right, let me figure this out real quick. You're gonna go on this journey with me, everybody. Oh, yeah, that kind of works. That kind of works. Okay, so remember that in math, if you see an equal sign, if you divide by something on one side of the equal sign, you got to divide on the other. It's just the rules of algebra. When we do that, the 1/2s are going to cancel. They're gone. The 12 squareds are going to cancel, and the only thing left on the right is the m. So that makes me happy. I want m, and that's the only thing left. On the left side of the equal sign, we got 12,000 divided by 1/2 divided by 12 squared. And yesterday people were asking, hey, does it really matter if I do it the way you do, or can I do 12 squared times 1/2 and then divide both sides by that? And my answer is yeah, either way is totally fine. Whatever works for you is going to work for me. I like to do it this way. I don't know why. It just looks neater, I guess. But if you've got a different way and you arrive at the same answer and it's mathematically okay, I'm 100% okay. All right, now comes the really hard part in this thing, and that's entering this into the calculator. So 12,000. And on my calculator, I might use parentheses for everything on the bottom. So I'm going to hit divided by for our thing here, and then everything on the bottom is going to get parentheses. And then let's see. Let's do 12 squared again. So 12 squared times a half. I like the decimal half better than entering 1 divided by 2. So I'm going to say times a half. And then I think I'm done with my parentheses on the bottom. Don't have anything left, so I'll close parentheses, and then I'll hit equals. And I get 166.67. 166.67. And then let's see, this is mass. So like our notes from yesterday, we should have kilograms as our answer. So what did we just do, and what did we just figure out? We figured out that an object is moving and has 12,000 joules of kinetic energy. We were told how fast it's moving, and we want to figure out what its mass is. And we plugged all that into the equation. We did our division, and we figured out the mass is 166.67 kilograms. Well, that's way bigger than a bird. 166 kilograms is like almost 400 pounds, I think. That's like it's like a bear or something. All right, so that's it. That's pretty much as hard as it gets for kinetic energy. Sometimes you're just finding the kinetic energy. I'd probably say that's what you do in like 99.9% of the time. Every now and then you might have to solve for the mass. In potential energy, we just used a variation of the work equation. All right, so after you get done with this, after your notes are all done and ready to go, hit submit in Google Classroom, and then life will be good. And then after you do this, you can't see it on here yet because class hasn't started for about 30 minutes or so. But after you do get done with this, you're going to tackle this assignment. I'm going to post it on Google Classroom for you, and then you can take a look at it. A lot of questions where you're not doing any math whatsoever, and then at the bottom there's some fill-in stuff and a couple math ones, but that's about it. All right, and that's your task for today, March 23rd. If you've got any questions, leave a comment on Google Classroom, and I'll get right back to you. Thank you so much, everybody, and have a wonderful day.